Okay, I think we can start with our last morning, and I'm going to introduce Thomas Körber from University of Vienna, that is going to speak about Ricci-pinched three-manifold and inverse mean curvature flow.
Yeah. Thank you very much, Alessandra, and for the introduction and also for the invitation. It's been really nice here. And yes, I'll talk about recent joint work with Husken, where we're going to focus on a conjecture of Richard Hamilton. So in Daniele's talk on Wednesday, we've seen how the condition of non-negative rigid curvature limits or does not limit the topology of a surface. And today we're going to see how this condition limits the geometry of a surface, of a Riemannian three-manifold, sorry. So we're going to consider throughout the talk a connected and complete Riemannian three-manifold. And now Richard Hamilton made the following conjecture. So I've also heard sometimes that this has been attributed to Thomas Wilmore, so I'm not so sure. But in any case, the conjecture is as follows. So we suppose that we have a manifold with non-negative Ricci curvature, which is non-compact. And now we're going to assume additionally that this manifold is Ricci-pinched, and this means that there is a positive number epsilon such that the Ricci curvature is greater or equal than the scalar curvature times epsilon times the metric. So if we have this assumption, which I'm going to call Ricci-pinched, then it follows that MG must be flat. Okay, so a few remarks are in order. So first of all, this condition over here somehow means that all eigenvalues of the Ricci curvature are uniformly comparable. So this means that the manifold is in a certain quantitative way isotropic. And now if you look at the conditions, surely you can't drop this condition over here because there's a lot of examples of non-compact Riemannian three-manifolds with non-compact non-negative Ricci curvature. But then you can also probably not replace this by something substantially stronger, because, for example, if you ask for a strict lower bound on the Ricci curvature, then the Bonnet-Meyer theorem tells you that the manifold has to be compact. So somehow this seems to be some optimal assumption that you could impose for such a theorem to hold. To give you an example of what this condition means is, a basic example of a three-manifold with non-negative Ricci curvature is to construct something like that. What you can do is that you take something like a paraboloid. So it kind of looks like this. And then you cross this with a line. And now we can warp this a little bit to make this, so this is going to be strictly convex, so in particular it has non-negative Ricci curvature. And now if you warp this manifold a little bit, then it's going to have positive Ricci curvature. But now this surface over here, this curves a lot in the direction of the circle, but barely curves in the direction of the line. And for this reason, this is not going to be Ricci-pinched. So this is not ruled out by this conjecture. Okay, so what I want to say is what motivated Hamilton to prove this conjecture. And here I want to mention two results. So the first one is an analog that he proved in extrinsic geometry. And this is the following. So if we have a two surface in R3, which is properly embedded and unbounded, and now you assume in addition that this is convex. So this is the extrinsic condition replacing non-negative Ricci curvature. And also that you can bound the second fundamental form from below by epsilon times the mean curvature times the induced metric. So this is the assumption replacing non-negative Ricci curvature. Then it follows that sigma is a flat plane. Okay, so this looks very much like the similar statement as this conjecture over here in extrinsic geometry. Only one thing that I want to remark is what gives you an idea that this conjecture might maybe be a little bit more subtle is the following. So if you look at the rigidity statement over here, then you can only have flat planes. But then there's multiple examples of a three-manifold being flat, of course. So you could have something like R3, or you could also have something like R2 cross a sphere, or you could also have something like R cross a torus. And of course, these spaces have different topology, but they also differ geometrically. So this one has Euclidean volume growth, this one has quadratic volume growth, and this one has linear volume growth. So also from a geometric point of view, these spaces are different. Okay, and the last thing what I wanted to say is that this conjecture is also an extension of a theorem that Richard Hamilton proved, which maybe I'm not going to write it down. So what he proved is if you have a compact Riemannian three-manifold with non-negative Ricci curvature, which is Ricci-pinched, then he showed that this is either smoothly isotopic to a space form with positive curvature, or it has to be flat. And what this conjecture over here says is that in this result over there, you could drop the assumption of being compact. All right, so this theorem that Richard Hamilton proved, this was proved using Ricci flow. This was, I think, very much the birth of using Ricci flow for such theorems. And is, of course, motivated to prove this conjecture over here using Ricci flow as well. And this is, in fact, what happened. And so this is what I want to talk about next. So the proof of this conjecture using Ricci flow. So we're going to, again, assume that Mg is non-compact. With non-negative Ricci curvature. And to describe the contributions here, I need to recall what the asymptotic volume ratio of Mg is. So I think we've already seen this in Daniele's talk. So this is simply okay, so you take a point P, you consider a geodesic ball of radius R, and then you divide this by R to the 3, you normalize it by the volume of a Euclidean unit ball. And now it turns out that by the Bishop-Gromov theorem, this limit over here as R tends to infinity exists. And it's between 0 and 1. If it's strictly bigger than 0, we say that the manifold has Euclidean volume growth. If it's equal to 1, then the Bishop-Gromov theorem tells you that you must be flat Euclidean space. Okay, so now the first result that I want to mention. So this was proved by Lott and by Manchun Lee and Peter Topping. So they showed that if Mg is Ricci-pinched and not flat, then it follows that the asymptotic volume ratio is strictly positive. Okay, so this result was first proved by Lott under the additional assumption that the manifold has boundary curvature, and then Lee and Topping showed later on that you can remove the assumption of boundary curvature. Okay, so this is already a pretty strong statement because it kind of rules out situations like those two in the case where the manifold is Ricci-pinched. And to prove this result, they constructed a solution of Ricci flow coming out of the space. And for this construction, they used the condition of it being Ricci-pinched. And afterwards, they performed some blowdown analysis of this Ricci flow solution and a topological argument, which shows you that the asymptotic volume ratio is positive. So this is a bit technical, but a very nice result. And after they proved this, there was the following theorem of Daruel, Simon, and Schulze, where they kind of proved the converse. So they showed that if Mg is Ricci-pinched and has positive asymptotic volume ratio, then mg must be flat. And of course, if you combine these two theorems, then you get a proof of Hamilton's conjecture. Okay, so this proof over here is also very nice. The idea is basically that you blow down the solution of Ricci flow constructed by Lott to obtain a solution of Ricci flow coming out of the asymptotic cone of mg. But then also, I think Darrell developed a theory of weak solutions of Ricci flow coming out of less regular spaces, so they could construct a self-similar solution coming out of the asymptotic cone. And then they perform pretty delicate stability analysis of these two Ricci flow solutions to show that they're close to each other. And from this then follows that this can only be the case if the manifold is flat R3. So in the end, what this also shows is that the solution that they constructed over here never exists, because these spaces that they're considering, so a class of spaces, is empty in the theorem over here. So in hindsight, this is a vacuous statement. Okay, so Miles Simon told me about this result, I think in March or something like that. And then he told me that he's always thought that RCD spaces are useless. But then when he proved this result, all of a sudden he kind of figured that, yeah, like in their proof, RCD and Alexandrov spaces play an important part. Yeah, exactly. And then I was not convinced, because I was kind of thinking I still think they're useless. So me and Hus can try to prove it a different way, and this is what I want to talk about today. So all right, so I want to talk about the proof of our conjecture using inverse mean curvature flow. Okay, so because I don't really know what to talk about today, I'll just give you a quick recap of inverse mean curvature flow. So we'll consider a Riemannian three-manifold, which is non-compact. And then we'll consider a surface which lives in this manifold, which has strictly positive mean curvature. And now we say that a family of smooth surfaces flows by inverse mean curvature flow if we have the following two conditions. So first of all, we say that the position of these surfaces change by 1 over the mean curvature times the normal direction. So the normal speed of the flow is given by 1 over the mean curvature. And of course, for this to make sense in a classical sense, you need that the mean curvature is strictly positive. And then the second condition is just an initial condition, namely that the initial surface is equal to the surface that we're starting from. Okay. So the most basic example that you could think of is if our manifold is flat R3. And then you look for a solution of inverse mean curvature flow coming out of a round sphere. Then the solution is just going to be given by a sphere of radius e to the t over 2, centered at the origin. So this is a solution of inverse mean curvature flow coming out of the unit sphere. So in this case, the radius of the sphere is just expanding exponentially. So there's nothing too interesting going on. What I want to remark is you can also, of course, flow the solution backwards in time, and that way construct a solution of inverse mean curvature flow coming out of a point in a certain sense. Okay, so the reason why inverse mean curvature flow got popular, I mean, there's many reasons, but two results I want to mention is, first of all, so in the 90s, I think Gerhard and also John Erbers proved a result that if you start with a surface with positive mean curvature, which is also star-shaped in Euclidean space, and then you flow it by inverse mean curvature flow, then the solution exists for all times, and eventually it looks like like this expanding sphere solution over here. Okay, and then to talk about the other contribution, I want to mention a proposition. So if we have a solution of inverse mean curvature flow, so maybe I'll call this proposition A. Then what you can show very easily, and this holds in every ambient Riemannian manifold, that if you compute the derivative of the area, then this is simply just given by the area. So the area evolves exponentially, what we can also verify in this example over here. And then the other thing is that you can also show that the Willmore energy has a nice evolution equation. So you can show that the Willmore energy evolves by -2 times the integral of the tracer second fundamental form squared, plus the Ricci curvature in direction of the outward normal, and plus the gradient of the mean curvature squared divided by the mean curvature squared. Okay, so this is one observation, and then the other one, which maybe I'm going to call proposition B, is they can also express the Willmore energy using the Gauss-Bonnet theorem. And then you see that this is equal to 16 pi times 1 minus the Euler characteristic of the surface, plus 2 times the integral of tracer second fundamental form squared, plus the Ricci curvature in direction of the outward normal, and plus the integral of Ricci curvature in the direction of the outward normal minus the scalar curvature. Okay, so what was observed by, I think, Giroux is that in this evolution equation over here for the Willmore energy, you have the Ricci curvature. On the other hand, you can get rid of the Ricci curvature using this formula over here. And if you put all of this together, you see that a quantity known as the Hawking mass is non-increasing in a manifold of non-negative scalar curvature. And this is the basic building block in the famous proof of Huisken and Illmann of the Riemannian-Penrose inequality. Okay, so on the other hand, to see why inverse mean curvature flow might be useful to prove this conjecture here, there's maybe two things you can observe. So first of all, if you have non-negative Ricci curvature, then this quantity over here is non-increasing, because, I mean, all of these terms are, of course, non-negative, and this term is also non-negative. So this holds when Ricci curvature is non-negative. And then on the other hand, you get the Ricci curvature over here, but you also get scalar curvature in this formula over here. So these two quantities seem to be important in this conjecture, are somehow captured by the evolution of the Hawking mass. Okay, so before I talk about how to use inverse mean curvature flow, there's, of course, the general problem of inverse mean curvature flow, that the flow develops singularities. And in case of inverse mean curvature flow, there's actually a lot of things that can go wrong. So first of all, if the mean curvature tends to 0, then the diffusion speed of this flow becomes infinite. So this might be problematic. Then you could also have singularities in the classical sense, that the second fundamental form blows up. Or also, because this flow is an expanding flow, what can happen is if you start with two spheres, which are not connected, and then, of course, both of them are going to expand exponentially. So if you wait a little bit, then these two spheres are going to self-intersect. And from this point onwards, you can't continue the flow, at least not in the class of embedded surfaces anymore. Okay, so this problem has, of course, been known for a very long time, and this led Huisken and Illmann to consider weak solutions of inverse mean curvature flow instead. So let me also quickly talk about this. So in order to define these weak solutions, the idea is that you use a level set formulation. So you take a function which is in the end going to be locally Lipschitz. And now we define ET to be the sublevel set of this function U. And now what we hope is that the solution of inverse mean curvature flow is going to be given by the level sets of this function, or of the boundary of the sublevel sets of this function. Okay, now the basic idea is that you now suppose you had a smooth solution, which is given that way, and then you rewrite inverse mean curvature flow in terms of this level set function. And this leads you to the following PDE, that the divergence of the gradient of u divided by the length of the gradient of u is equal to the length of the gradient of u. Okay, so this is maybe not the nicest PDE that you've seen in your life, because this is degenerate and also singular, but it's also not horrible. It turns out that you can still make sense of this equation in a variational sense. And this is the idea that Huisken and Ullmannen had. And what they could prove is the following. So I'll summarize the most important properties. Okay, so we assume that there is a subsolution of inverse mean curvature flow. And I don't want to really define what this means, but essentially it just means that you can find a flow of surfaces in your manifold that somehow flows quicker than inverse mean curvature flow. So this somehow gives you an upper bound for how quickly a weak solution of inverse mean curvature flow could flow. So if you have this assumption, and now if you take a pre-compact open set in your manifold, and you additionally assume that the boundary of this open set, which I'm going to call sigma, is outward minimizing. So I'll say something about this in a moment. Then it follows that you have a weak solution of inverse mean curvature flow with initial data being equal to the surface sigma over here. Okay, and let me also mention some properties of this weak solution. So first of all, we have that sigma t is of class W22 and also C11. So this means in particular that the surfaces are almost C2 in a certain sense. Then you know that the flowing surface is outward minimizing. Okay, and outward minimizing means that if you enclose the surface in any way, then the enclosing surface is going to have at least as much area as the surface over here. So it's going to be important later on. And it turns out that this is somehow the correct variational formulation of inverse mean curvature flow. And for this reason, you also need the initial surface to be outward minimizing, so you can understand this as some sort of compatibility condition that needs to be verified for this flow to make sense variationally. Okay, then the third thing that you have is that the mean curvature is strictly positive almost everywhere for almost every t. And moreover, that the logarithm of the mean curvature is in W12. So this means in particular that the right-hand side of this proposition over here makes sense. And actually what you can show is that this proposition A at least holds in the distributional sense for this weak solution of inverse mean curvature flow. So in weak inverse mean curvature flow retains nice properties that a smooth solution had. So I'm just going to write the proposition A holds. Okay, so we have these properties. But so this, what the idea of this, yeah? Mm-hmm. Yeah, so I was about to say, yeah, no worries. So the idea of this weak solution is that it allows for more flexibility. So topology can change, the number of connected components can change. And if you look at this example over here, the point is when these spheres are very close to each other, this is not going to be an outward minimizing surface anymore. So in fact, what happens is this weak solution flows a little bit like this. And then at some point, they're so close together that you can connect them in a way that the connected surface is gonna have as much area as the other surface. So what happens is that a catenoidal bridge forms between those two spheres. So it kind of jumps over this volume over here. So it doesn't continue like the smooth flow. It forms this catenoidal bridge, and afterwards the flow kind of continues like this in a smooth way. Absolutely, yeah. So it flows for a little bit until it ceases to be outward minimizing, then this catenoidal bridge forms, and afterwards the flow continues in a smooth way, basically. Yeah. Exactly. So also in this example over here, we've seen that the number of connected components can decrease. And in most applications, you don't want the converse to happen. And usually you can't really rule out any topology changes for weak solutions of inverse mean curvature flow, but there's at least one thing that you can show. And this is if mg is simply connected. So this would be the case in the case of R3. And if sigma is connected, then no new connected components can form. So in that case, you know that sigma t remains connected. Okay, so now I want to specify this theorem to our situation. And here I want to mention a result of Mari, Rigoli, and Setti. And this builds on previous work of Roger Moser. So they showed the following. So now we make the additional assumption that the Ricci curvature is non-negative, as in our situation. And now for simplicity, I'm just going to assume that the manifold has well-defined volume growth. So I'm going to assume that there is a constant alpha, which is bigger than 0, such that the limit, again, we take a geodesic ball of radius r and divide it by r to the 1 plus alpha. And I'm going to assume now for simplicity that this limit over here exists and is positive. So then this number alpha just tells you the growth of volume. So if alpha is equal to 2, you have Euclidean volume growth. If alpha is equal to 1, then you have quadratic volume growth. But what's ruled out in the theorem over here is linear volume growth. So I'm going to assume that alpha is strictly bigger than 0. Okay, and then we have the following result that you can in fact construct subsolutions of weak inverse mean curvature flow. So if I take a point P in the manifold, then there is a function rho, which is locally Lipschitz. And they call this function rho fake distance. I'm going to explain in a moment why. And this function has the following property. So rho of P is equal to 0. And apart from that, rho is strictly positive. Okay, then moreover, if you consider the set, so if you define sigma t to be the set of surfaces where rho is equal to e to the t over 2, then this is a weak solution of inverse mean curvature flow. And this maybe also gives you an idea why this function rho is called fake distance, because this is the same solution as for Euclidean inverse mean curvature flow. So somehow this function rho is modeled on the Euclidean distance function. Okay, and this also explains the following, which will be important later on. So we know that so if these fake distances are modeled on Euclidean distances, this means that a ball with respect to this fake distance has the same volume as a Euclidean ball. But we know that volume grows slower in manifolds of non-negative Ricci curvature than in the Euclidean space. And for this reason, such a fake ball has to be larger than a geodesic ball in the manifold. So we know that a geodesic ball of radius p is contained in a fake ball of radius p. But on the other hand, this condition over here also gives us a lower bound on the volume growth in our manifold. And this in turn tells us that this fake ball over here is again contained in a geodesic ball. So this is going to be contained in a ball of radius, some constant, which I'm just going to call C maybe, times r to the 2 over alpha. And in particular, if we have Euclidean volume growth, then alpha is equal to 2, and geodesic balls and these fake balls are comparable. Okay, and then we have two more properties that come from the fact that this is a weak solution of inverse mean curvature flow. And the first one is that if we compute the area of the boundary of such a fake ball, then this is simply equal to 4 pi times r squared. And moreover, what you can also show is that this set over here is outward minimizing. So this again follows from the property of inverse mean curvature flow. Okay. So what I want to emphasize is that this result over here gives you the existence of a weak solution of inverse mean curvature flow in a large class of manifolds with non-negative Ricci curvature, and in particular, it makes it applicable to our case here. And now I can finally talk about our proof. Or maybe I should first say what we're going to prove. So what we show is the following theorem. So this is by Husken and myself. So we're going to assume that we have a manifold Mg, which is three-dimensional, connected, complete, non-compact. We're going to assume that the Ricci curvature is non-negative and that it is Ricci-pinched. And then we can show that Mg has at most quadratic volume growth. Okay, so what this tells us in particular is that the asymptotic volume ratio must be equal to 0. So we recover the result of Daruel, Simon, and Schulze. And I have a feeling that you maybe can improve this result a little bit to show that such a manifold has at most linear volume growth. But still, we still have to rely on this result of law to obtain an alternative proof of the conjecture of Richard Hamilton, because actually it turns out that you can't study the case of linear volume growth using inverse mean curvature flow. Because if we go back to this example that we had before, where we have R cross a torus, then the space is foliated by these tori over here, which are minimal. All of them have the same area. So this is not compatible with exponential area growth and the leaves of inverse mean curvature flow being outward minimizing, because at some point the flowing leaves would have area larger than the torus, but this can't be the case. And for this reason, in such a space, you can't have a solution of inverse mean curvature flow. So at least to study the case of linear volume growth, you would have to develop a different technique than the one we're using. So this is something I'm thinking about, but haven't really come up with a solution with. Okay, so in the remaining time, I want to talk about our proof, which is hopefully not going to take too long. Yeah, sorry, and over here I forgot to say that, of course, we have to assume that the manifold is not flat. Okay, so we suppose that we have such a MG, which is not flat. And then the first observation is that we have a point such that the Ricci curvature can't identically vanish at this point, otherwise the manifold would be flat. So in particular, this means that the scalar curvature at this point is non-negative, is positive. But then this also tells us that the Ricci curvature at this point, which is bigger than epsilon times the scalar curvature times the metric, must also be strictly positive. Okay, now there's this result of Chu, which is building on previous result of Shane and Yao in a special case of the theorem of Gang Liu that Daniele mentioned, which then tells us that MG must be diffeomorphic to R3. So you can prove this using minimal surface techniques. This is actually not too difficult. Okay, so at least we're in this nice situation where MG is simply connected and we don't have to worry about new connected components to form. Okay, now there's the following lemma that I want to emphasize. So if we have a surface in M which is closed and two-sided, then we have the following two options. So the first one is if the genus of sigma, if this is bigger than 1, then we can bound the Willmore energy from above by 2 times the length of the tracer's second fundamental form integrated, plus the Ricci curvature in direction of the outward normal. So this is the first statement. And then the second statement is, in case the genus vanishes, then we get a different lower bound. Namely, we can show that 2 times the integral of the Ricci curvature is bounded from below by epsilon times 16 pi minus the integral of the mean curvature squared. Okay, so this lemma is going to be really important in our proof. It's, apart from this statement over here, the only time where we use the assumption of it being Ricci-pinched. So I should maybe give some emphasis to this. Okay, so the proof is simply using the Gauss-Bonnet theorem. So we have that we can write the Willmore energy as 16 pi times 1 minus Euler characteristic of the surface plus 2 times the integral of tracer's second fundamental form squared plus Ricci curvature plus the integral of Ricci curvature minus scalar curvature. Okay, so now if the genus is equal to 0, or if the genus is greater or equal than 1, then we can estimate this term over here from below by 0. So then this is less than 0. And then because we have non-negative Ricci curvature, scalar curvature has to be at least as large as the Ricci curvature. So we also can estimate this term from above by 0, and then we get our estimate. Okay, so now on the other hand, if the genus is equal to 1, then we can just use the assumption that the Ricci curvature is non-negative and estimate this from below by 16 pi. So we also throw away this term over here. So we just end up -2 times the scalar curvature. And now we use the assumption that the manifold is Ricci-pinched, and then we can estimate this from below by 16 pi -2 times the integral of the Ricci curvature, sorry, 2 times epsilon times the integral of Ricci curvature. Okay, and then we just rearrange terms and we're done with the proof of the lemma. Okay, so this is the first observation, and from this lemma, it follows that you can construct a solution of inverse mean curvature flow where the Wilmer energy decays very rapidly. So we have the following lemma, that there exists a weak solution of inverse mean curvature flow such that the Wilmer energy decays exponentially. Okay, so let me prove this. Okay, so again, we consider a point of strictly positive scalar curvature, which we have because the manifold is not flat. Now, if you take a very small geodesic sphere around this point, they can show that the Wilmer energy has to be strictly less than 16 pi. So we take a ball of a small radius p. And this behaves approximately like 16 pi minus scalar curvature times r squared plus an error of r cubed. So if you take r sufficiently small, this is going to be less than 16 pi. So we take this little point over here, take a geodesic ball, and now we enclose this by its outward minimizing hull. So this is BRP. And now we take the minimizing hull, which might be this geodesic ball itself. But the point is, if you consider this minimizing hull, then this minimizing hull has less area, and whenever the surface touches, the mean curvature is the same as the original mean curvature. But whenever the surface is disjoint from this geodesic ball, the mean curvature is equal to 0. So when you form this minimizing hull, the Wilmer energy can only go down. So we know that this is less or equal than the Wilmer energy of this surface sigma over here. Okay, so now the idea is that we start inverse mean curvature flow from the surface over here. And now the first observation is that we know that 16 pi minus the integral of the mean curvature squared, that this is greater or equal than some constant delta 1 times the integral of the mean curvature squared for some positive number delta 1. Because the reason is the left-hand side over here is strictly positive. So if we make this delta 1 over here sufficiently small, then this estimate is for sure going to hold. Okay, now on the other hand, we know that the Wilmer energy is non-increasing along inverse mean curvature flow. So if we start the flow, then we know that this term over here goes up, while this term over here goes down. So this estimate is also going to hold for all t. So you can also write a little t over here. Okay. And now we're almost done. So now we compute the evolution of the Wilmer energy. And as I said, this is given by -2 times the integral of the tracer's second fundamental form plus Ricci curvature plus the gradient of the mean curvature squared divided by the mean curvature squared. So we get rid of this term over here. And now we use this proposition over here. I hope that I didn't erase it. Yeah. So in the case where the genus is equal to 0, we can simply estimate this from above by minus the integral of the mean curvature squared. So this happens if the genus of sigma t is greater or equal than 1. Okay, then in the other case, we throw away this term over here. Then we can estimate this by epsilon times 16 pi minus the integral of the mean curvature squared. But now we also use this estimate over here. And then we get that this is less or equal than epsilon times delta 1 times the integral of the mean curvature squared. Okay, so in either case, we see that the Wilmot energy decays exponentially, but maybe not with this rate that I've claimed. But now the point is that the smaller the Wilmot energy gets, the better this estimate over here becomes. And in particular, if we wait for a very long time, then we can actually replace delta 1 over here by 1 over epsilon, if this is very close to 0. So if we wait long enough, then the decay is going to be exponential. But it's not going to be better than exponential, because it could always be that the surface always has the topology of a torus, and then this estimate over here doesn't get better. Okay. All right, so maybe I'll continue up here again. Okay, so at this point, I want to remark that now we already have reproven the result of Daruel, Schulze, and Simon, because as a result of Agostiniani, Mattia, and Mattieri, I'm just going to write, which tells us that we can bound the Wilmot energy of this flowing surface from below by 16 pi times the asymptotic volume ratio. So there's also an alternative proof for this from Xiaodong Wang, I think. And we know that this decays exponentially, so this estimate can only hold true if the asymptotic volume ratio is equal to 0. Okay, so if we just wanted to reprove the result, we're already done now. But I told you that we can prove a little bit more, namely that the volume growth can be at most quadratic. So let me quickly show you how to do that. And the idea here is, if the Wilmot energy is very small, then this means that the mean curvature has to be very small on the scale of the area. But this in turn means that the surface must flow very quickly. And this kind of means that the surface must sweep out volume a lot quicker than it increases area. And this in turn gives you, it gives you an upper bound on the isoperimetric profile. And this you can use to rule out quicker than quadratic area growth. So let me show you how you can do this. So the idea is that we start with Hurley's inequality. So we estimate the area squared from above by the integral of the mean curvature times the integral of 1 over the mean curvature. And now we use Hurley's inequality again. And we can bound this from below by the Wilmot energy, or the square root of the Wilmot energy, times the square root of the area, times the integral of 1 over the mean curvature. Okay, now we know that this term over here decays exponentially, this one grows exponentially. So we also know that this one grows like e to the 2t. So what we deduce from this is the following, that the integral of 1 over the mean curvature is greater or equal than some constant, which I'm not going to specify, times e to the 2t. Okay, now on the other hand, of course, if you compute the time derivative of volume, then this is when the flow is smooth, simply given as the speed of the flow integrated over the boundary of the surface. Now, of course, the inverse mean curvature flow could dump, but then the volume increases even more. So the integral of this term over here gives you a lower bound for the volume enclosed by the surface sigma t. Okay, so from this, it follows that the volume enclosed by the surface sigma t, which is the set et, that this is greater or equal than some constant delta 3 times e to the 2t. Okay, and in particular, this means that if we take the limit as t tends to infinity, or the lim inf of the volume enclosed by the surface sigma t divided by the area of sigma t squared, that this is strictly positive. And this somehow means that you need less area to enclose a volume than in Euclidean space, because in Euclidean space you would have to have 3/2 in this exponent over here. So the exponent is better than in the isoperimetric inequality in Euclidean space. Okay, now to analyze this further, we use this result of Mari, Rigoli, and Setti. So the idea is that we have this point P. So this is our surface sigma. And now we want to construct a comparison solution. And in order to do this, we used these fake distances that they've introduced. So we take a small fake ball where rho is equal to delta. And then we also take a large fake ball which encloses the surface. So here rho is equal to delta to the -1. And now we start inverse mean curvature flow at this little ball over here and that large ball over there. And because of the maximum principle, these solutions remain distinct. So for this reason, what we can show is that the fake ball of radius delta to the e to the t over 2, that this is contained in the set et. But again, this set over here is contained in the fake ball of radius delta to the -1 times e to the t over 2. Okay. Okay, so now I use this estimate to estimate the volume from above of this inverse mean curvature flow. So this is less or equal than the volume enclosed by this fake ball. But because of the Euclidean, because of the volume growth that our manifold has, we can estimate this from above by the size of a geodesic ball. So this is going to be less or equal than the size of a geodesic ball, where I now have to times this exponent over here by 2 to the alpha. So the radius is going to be delta to the -2 over alpha times e to the t over alpha. Okay, so this is one basic estimate. And then the other estimate that we have is, now we want to estimate the area from below. And we know that the surface sigma t encloses the fake ball of radius delta times e to the t over 2. We also know that this is a weak solution of inverse mean curvature flow. So in particular, this is outward minimizing. So we can estimate this from below by the area of the boundary of this fake ball. And this is then given as, 4 pi times delta squared times e to the t. Okay, now we just reparameterize this e to the t. So we write, wait, maybe this is a little bit too high. So now we take r equals e to the t over 2 as a radius. And now if we rewrite all of this, so we look at this, where did I write it? So we look at this inequality over here, and we replace et by this estimate over here. And we replace sigma t using this estimate over here. So what we then get is that if we take the limit, or the lim inf, as r tends to infinity, and now I'm just going to forget about this delta for a moment over here. So this becomes a ball of radius. Wait, sorry. So I wanted to take r equals e to t to the alpha. So we have a geodesic ball of radius p. And this term over here becomes r to the 2 alpha. Then we know that this limit is strictly greater than 0. Okay, but on the other hand, we knew that what we also know, what we assumed is that our volume growth is given by r to the 1 plus alpha. Okay, so now if alpha was strictly greater than 1, and this is bounded from below by 0, then 2 alpha is greater than 1 plus alpha, so this would have to tend to 0. So this estimate over here can only be true if alpha is less or equal than 1. And this precisely corresponds to the case where you have at most quadratic area growth. All right, I'm at the end of my talk. Thank you very much.
For your very nice talk. Questions?
Maybe a very naive question for the like a 4-dimensional case. Is there a Hamilton type problem?
Yeah, I don't know. I mean, maybe a natural conjecture that you could ask. So I think what Darrell, Schulze, and Simon proposed in their paper is that you replace non-negative pinched Ricci curvature by 2-pinched Ricci curvature. I forget exactly how they define that, but at least you need to impose some sort of strong assumption on the Ricci curvature, right? Because you could just have a manifold with vanishing Ricci curvature, which is not flat in 4-dimensional space. So somehow you need to impose a stronger curvature condition than just asking for a condition on Ricci curvature. And I also don't know if it's reasonable to conjecture that such a manifold would have to be Ricci flat. I don't know if there's counterexamples to that. So at least I haven't studied it, but they pose some sort of conjecture in their paper. But yeah, I forgot what.
So
exactly
what about like there's a condition that the manifold is locally conformal flat? Do you know any result in that direction?
I don't think there is a result, but yeah, maybe so if the wild tensor vanishes, say, and then if you could show that if it's Ricci-pinched.
Yeah, because actually in your math you're using like the Gauss-Bonnet.
Yeah.
So it's highly restricted on the 2-dimensional case.
Exactly, yeah.
So okay.
Yeah, so there's certainly no way that this would extend to higher dimensions, but maybe the Ricci flow could. But
by the way, for the another you using the factor distance theorem by, is that the result is also true in high dimensional?
Yeah,
case?
this is true in all dimensions. Yeah.
Okay.
So I mean, basically, you could use inverse mean curvature flow to study manifolds with non-negative Ricci curvature in higher dimensions, but then I guess you still get a monotonous quantity if you look at a Hawking type quantity, because you still have this basic estimate on the Ricci curvature. But then, yeah, it's probably more complicated how you would bring scalar curvature into play, because then you can't use Gauss-Bonnet anymore. So yeah, it seems very much restricted to the 3-dimensional case.
Okay. Another maybe in the last line of that blackboard, what kind of holding inequality you used?
Over here?
Yeah. It's like something maybe 1/2 missing.
Wait,
I'm not sure.
I just write.
In the second inequality, there is something missing, I guess.
Ah, yeah, sorry. Yeah.
Okay, yeah.
Yeah.
Thank you.
Yeah.
Other questions?
A very quick question. When you first mentioned that you could assume a priori that the manifold is diffeomorphic to R3,
Yeah.
It's just due to the fact that there is a point with positive scalar curvature. It's just for that reason. So you're not using all the Ricci-pinched condition.
No, yeah, you just need you need a point of positive Ricci curvature, not of positive scalar curvature.
You would need a point of positive Ricci.
Yeah, yeah.
Okay.
Yeah. So this is and this is ensured by the fact that that you use the Ricci-pinching condition, because I mean otherwise you could have a point where maybe one direction of Ricci yeah, exactly, yeah.
Ah, okay. You have okay, you need the Ricci curvature that's positive in all directions.
Exactly, yeah.
Okay, and then you use the classification result value, or you because you mentioned someone else.
This is actually less subtle than the result of two, because the idea is so you know the Shane and Yao paper where if you have positive Ricci curvature, then
okay, but it's for all points.
Yeah, exactly. But the idea is if you have one point of positive scalar curvature, then you can kind of distribute this one point of positive Ricci curvature. You can kind of perturb the metric. Then the Ricci curvature becomes a little less positive at this point, but you can like make it positive along a path, if that makes sense. So if you have one point of positive curvature, you can use a deformation of the metric to make it as positive as you like anywhere else. So it gives you enough flexibility to make this result of Shane and Yao work. So actually the proof of this result of 2 is 1 page or something like that. He just reduces it to the Shane Yao proof.
Okay, and the one you mentioned was Zhu.
Zhu, yeah.
Okay, that was the one who applied this argument you just
exactly
said.
Yeah.
I see. Okay,
yeah.
no, I didn't know.
Yeah.
Okay, thank you.
So it just says that if you have a 3-manifold with positive Ricci curvature, then it must be diffeomorphic to R3. And the idea is somehow that, say you had some sort of topology, then you find a minimal surface that encloses this topology, roughly speaking. But then this contradicts the stability inequality that you could find a stable minimal surface because of positive. Yeah. And then exactly if you have one point of positive Ricci curvature, then you perturb it in a way such that the minimal surface would still see this positive Ricci curvature. This is the idea of that proof, yeah.
And so in particular, you're using also the Ricci-pinched condition for having this positive.
Yeah, thing. I mean, this result is false otherwise, of course, because you could take something like a paraboloid times S1, I think. So this has non-negative Ricci curvature, it has positive scalar curvature. But yeah, it's not diffeomorphic to R3. Yeah.
The technical question, when you said it's that you deduce that the volume growth is at most quadratic, you say that for any radius that for any geodesic balls have the limb sup
exactly,
of the volume growth, that's the limb sup.
The limb sup is wait.
Because it seems to me that actually you find a sequence of radii where the volume growth.
Wait, no, that the limb inf has
okay.
Yeah. You could have theoretically like quicker volume growth somewhere, but the limb inf has to
exactly. Okay.
Yeah.
So okay.
Yeah.
Okay, so it's slightly weaker, right?
Exactly.
Okay.
Yeah.
Okay, we arrived to the final talk of this workshop, and it's my pleasure to introduce Marco Pozzetta from the University of Napoli. And he's talking about isoperimetry and geometric rigidity on manifold with non-negative curvature.
Okay, thank you, Alessandra. Thanks to the organizers for the invitation. And so, yeah, this was the title. And okay, so the purpose of the talk is to discuss some implications in the following sense. The implication, okay, there is an obvious implication that we can ask, is that answers to the following question: in which way the geometry of a manifold can influence the isoperimetry of the manifold? And this is not too surprising, but I would like also to discuss the other implications. So, is it possible to deduce something on the geometry, on the global geometry of a manifold, starting from a sort of we'll speak of a global knowledge of the isoperimetry of a manifold. And when I say global knowledge, I mean some assumptions on the global behavior of the isoperimetric profile. If you don't know what the isoperimetric profile is, don't worry, I will define it in a minute. So, and as this question mark points out, the point is that the second implication is way less understood. And we will try to discuss. I would like to give you basically an overview of questions and answers one can do in this topic. And in order to discuss this implication, we will focus on manifold spaces with notions on non-negative curvature. So I will give you some preliminaries about the geometry of such spaces and definitions about the isoperimetric problem, and then the talk will be divided into two parts. In the first part, we will focus on the case of non-negative Ricci with so-called maximal volume growth, and in the second one, non-negative sectional curve with so-called minimal volume growth. So okay, let's start with the setting. So we will always consider in this talk a non-compact complete Riemannian manifold connected, if you want. Capital N is going to be the dimension greater or equal to 2, and not only it will be non-compact, but also it will have an infinite volume. Okay, and I will use the absolute value to denote the volume of any set, also manifolds. Okay, now the point is that at some point we will see that it will be necessary actually to speak about metric measure spaces. Okay, so more generally, we will consider metric measure spaces that are triples MD, so metric space, endowed also with a measure that is always going to be the n-dimensional Hausdorff measure. And the most basic example, of course, is the case of a Riemannian manifold. Take a Riemannian manifold, forget about the smooth structure, and just consider the Riemannian distance and the Riemannian volume measure. Now, for all the talk, if you are not familiar with metric measure spaces, you can always think in your mind about a manifold. But we will see that it will be actually necessary to speak about metric measure space. So I will try to convince you that some classes, as we said before, of metric measure spaces are not completely useful, are not completely useless. Useless. Okay. So yeah, I know. Okay, so it's gonna know. So let's move on. Okay. So as said, we need definitions of lower bounds on the curvature. And now probably anybody here knows what the Ricci curvature is, but anyway, if you want, you can define the Ricci curvature as the operator that you put here to verify this identity for any smooth function on a manifold. And actually, you can codify the fact that the Ricci curvature is bounded from below by a constant that is always going to be 0 in our case, by prescribing the validity of this inequality. That is called the Bochner inequality. Whenever you have this inequality, then you can say that your manifold has non-negative Ricci curvature. And now you don't need to remember this inequality. We will never see it again, but let me just, if you're not familiar with it, let me just point out that encoded in this inequality, you have as corollaries many structural properties on your manifold, just assuming this inequality. And we will focus on corollaries, on the consequences, on structural consequences that follow from the validity of this inequality. Now, this is a differential inequality. So even if I don't want to tell you the details, you can believe that you can prescribe a sort of weak integral version of this Bochner inequality, just multiplying by test function, let's say, and integrating. You can prescribe the definition of having Ricci bounded below from 0 whenever a weak version, an integrated version of this inequality holds. And in particular, you can do this on a metric measure space. And this gives rise to the definition of so-called RCD 0n spaces. So there are metric measure spaces with let's say non-negative Ricci. So again, if you want, or whenever I will say RCD space, you can think of a Riemannian manifold with non-negative Ricci. It's not a problem. Of course, this is the theory well developed in the last years by many authors. Okay. Again, we don't really need the very definition, but consequences. Before telling you the structural consequences you have on the space when you assume this definition, let me just tell you one example. Exactly, a very simple example. Cones. Okay, so what is a cone? This is the wildest metric measure space that is not a Riemannian manifold that we will see in this talk. So okay, so we are not very far from Riemannian geometry. So what is a cone? Just to define it properly, and in an intrinsic way, take a compact metric space L that stands for link, that is going to be the cross section of the cone, and then the cone built over L is just 0 plus infinity times L quotient the points with the first coordinate equal to 0 with the suitable distance. Okay. Again, if you are more familiar with the Riemannian geometry, you can think that L is a smooth manifold with some metric GL. Then the cone is exactly the manifold with some singularity, with at least one conical singularity, endowed with the metric dt squared q t plus t squared GL. Right. So just like if you are writing the metric tensor on Rn in polar coordinates. Right. So this is a cone. Okay. And this is again the basic metric measure space that we will find later. Now, okay, in the class of these spaces with non-negative Ricci curvature, as also reminded by Daniele the other day, but also by Thomas before, we have some consequences on the structure of the manifold, and especially on the volume growth of balls. So we already heard these things in the other talks, but let me remind again this properties very, very quickly. The first consequence, so whenever you have your space with non-negative Ricci, your manifold with non-negative Ricci, then there holds the Bishop-Gromov theorem, generalized by Sturm and Otta to this class of spaces. So in particular, you consider the map sending R to the quotient volume of a ball of radius R of any center over the volume of the Euclidean ball. Omega n is the usual symbol for the volume of the unit ball in Rn. Well, then this ratio is decreasing, is non-increasing, and less than or equal to 1. So in particular, we deduce two things: that we can take the limit as R goes to plus infinity, and also that for any R, this is less than 1. So we have actually an upper bound on the possible volume growth of the volume of balls, right? For sure, the volume of a ball is less than the one of the Euclidean space. We have an upper bound. So it makes sense to make the following definition to define the asymptotic volume ratio that we already saw before. It is just the limit as R goes to plus infinity of this ratio. In general, it's going to be between 0 and 1 because it is less than 1 always. And so we can say that when AVR is greater than 0, the manifold, your space, has Euclidean volume growth. Indeed, we already said that the volume of a ball is less than the one of a Euclidean ball, but when AVR is greater than 0, then actually the two volumes are comparable, right? So the volume of growth is at least a constant times the volume of Euclidean ball. And we can also have rigidity, in particular in the following sense. Let's say that you have again your space with a negative Ricci and positive AVR. And let's say that actually at some point this ratio becomes constant. So precisely you find a ball whose volume is exactly AV, so the limit time omega n R to the power n. Then this means that from that radius on, this ratio is going to be constant, right? So the volume of a ball is going to be always proportional to the volume of Rn. So you can already believe that from that radius on, your space should be somehow invariant, right, with respect to dilation, with respect to homotheties. And indeed, whenever you find such a ball, then actually you have rigidity in the sense that your manifold is actually a cone. Your space is a cone. And as said by Thomas before, if the manifold is actually smooth, then actually M is Rn because it is the only smooth cone. But otherwise, you find a cone. So the basic picture that I want to keep here for the future, it is the first case. The case of positive AVR, the picture one could have in mind is the one of cones, or maybe manifolds that on a large scale they resemble cones. right? So this is the first class. Now, not only we have an upper bound on the volume of both, but I said the other day, we also have a possible minimal volume growth on these spaces. This was an argument first introduced by Calabi and Yao, and it is based on the so-called Laplacian comparison. So it can, thanks to the Laplacian comparison by G, you can be generalized to these spaces. So, but anyway, take your manifold with non-negative Ricci, then for sure, at least for large radius, the volume of a ball grows at least linearly. So in this case, what is the picture one can have in mind? The other world, the world of the minimal volume growth, is going to be the linear volume growth. The picture one can have in mind is the one of a cylinder, for example, right, where the growth is linear, or maybe of a manifold that could be asymptotic, right, asymptotic to a cylinder, and again the volume growth is linear. Okay, so we have a maximal and minimal volume growth under non-negative Ricci assumption. Okay, and yeah, probably, and this is indeed the picture that will be enforced for the rest of the talk of the two possible worlds. And okay, this is about so the geometric setting where we are going to set up our variational problem. And now I need to define the variational problem. That is the isoperimetric one. And so I need the definition of perimeter. Perimeter is the following. It's just a way of measuring, right, the n-1 volume of the boundary of a set. Okay, you can do this on a manifold or on a metric measure space if you want, by relaxation. In the following sense, consider the characteristic function of a set of finite volume. Why not? Okay, so this is the characteristic function, and try to approximate it with the Lipschitz function in L1 in the best possible way, where best means trying to pay the least possible value of the L1 norm of the gradient. Since you are integrating the L1 norm, you're only integrating here on where you have some slope. When you pass to the limit, you can believe that in the limit we will find a good approximation of the volume of the boundary. Okay, and of course, if you are on a metric measure space, you can ask, yeah, but how do you define the gradient? I don't actually need the gradient. I only need the absolute value of the gradient. And in that case, I can take just the lim sup of the modulus of the difference quotient. And in that case, this on a manifold gives again to you the absolute value of the gradient, right? So I have a notion. Again, you don't need to remember the very definition, but just the fact that on any space we will consider, we have a good notion of perimeter of sets. So this is the picture, and we have perimeter. After we have perimeter, we can define. Yeah, of course, whenever you have a smooth set in a smooth manifold, the perimeter is just the n-1 dimensional area, right, of the boundary. Once we have perimeter, we can define our variational problem. So the isoperimetric problem is the following. You try to minimize the perimeter among sets having a fixed volume. So take a volume between 0 and plus infinity. You want to study, in a very general sense, you can ask many questions. The minimization, try to minimize perimeter of E among subset of that fixed volume. Any minimizer, we will call it isoperimetric set. And we will be interested in the behavior of the isoperimetric profile. The isoperimetric profile is a function of one variable that for any volume tells you what is the infimum of the problem. Maybe I will write it down to remember it in general. So the isoperimetric profile of a space at volume V is just the infimum of perimeter of E among sets having that volume. Okay, having that volume. So maybe, for example, we can recall two possibilities. The easiest possibility in the positive AVR case, for example, is the one of the Euclidean space. The Euclidean space is the easiest manifold with positive AVR, right? And we know that in case you take Rn, the profile is exactly the perimeter of a ball having volume V, right? And it is a dimensional constant that I want to write it explicitly, n omega n to power 1 over n, and then volume to the correct power that makes, the problem is scale invariant, n minus 1 over n. So the picture for the isoperimetric profile of Rn is actually this one as a function of the volume, right? Instead, in the case in the other world, in the case of the linear volume growth, in the case of a cylinder, for example, what is the typical picture of an isoperimetric profile? It is the picture of a bounded isoperimetric profile. So if I have a cylinder, for example, cylinder, the typical picture should be something like this, where the profile is bounded. Why is it bounded? Because take any volume large as you like, but well, that for that volume I can take a piece of the cylinder, and the perimeter is just going to be at most twice the area of the cross section of the cylinder, right? So in any case, it is going to be bounded. So we have two worlds. We have the problem and two possible typical pictures, let's say, at least that I can hope for in the two settings. So now I come to the final preliminary. Do you see something in common between these two pictures? The answer is yes. And it is a theorem that I will not discuss today. It is a result in collaboration with Antonelli, Pasqualetto, and Semola that is actually coming after many results, starting in the 80s by Bavard, Pansuo, also Gallo, it's not written here, Bale, and more recently Mondino, Nardulli, that tells to you that actually the profile is concave, indeed, as in the picture. Is concave. More precisely, if you have your space with non-negative Ricci, even if you take the profile and you raise it to the spontaneous power, right, that is n over n minus 1. It is the power that makes the profile of Rn linear. Even if you raise it to that power, then the function you get is concave. There is one more assumption about the volume of balls that I'm not going to discuss. If you are interested later, I will tell you more. So this is the final preliminary. I will not discuss this. I will use it as a tool later. So now we can pass to discuss the first realm. So the one of positive AVR and non-negative Ricci. If you want the results I will tell you about are contained in a couple of works with Antonelli, Pasqualetto, and Semola. And if you are more interested, I wrote a survey on this stuff more recently. So the main theorem I want to tell you in this case is the following. It is an isoperimetric inequality with rigidity in the first setting. So take your space with positive AVR. Well, then you know that the perimeter of any set is greater than constant time volume to the correct power. It's very similar to the isoperimetric inequality on Rn, right? Except that in place of 1 inside the parentheses where there is omega n, there is also AVR, exactly. So when AVR is equal to 1 and you are Rn, you recover the isoperimetric inequality of Rn. This holds for any set, and equality is achieved by a set if and only if you have rigidity, not only of the set, but also of the space. So I have equality for a set if and only if the manifold is actually a cone, the space is a cone, and is a ball. Now, in the last years, there have been many proofs at different levels of generality for this theorem. So the statement I said is in the work in collaboration with Antonelli, Pasqualetto, and Semola. But first, in the smooth case, there have been progresses proving versions in the smooth case on smooth manifolds for this theorem by Agostiniani, Fogagnolo, and Mazzieri. Then again by Fogagnolo and Mazzieri, and by Brandle also. And there have been also proofs also with some notions of rigidity also on much more general spaces. So let me mention all the people who contributed. They are Balloga and Cristalli and Cavalletti Manini, who proved on other classes of metric measure spaces this result. And then combining with a more recent result also in collaboration with Ivan Violo, we have a generalization of this theorem, which is based on a very important paper by Cavalletti and Manini, actually. But okay, I want to discuss the statement above, where you can think you are on a manifold if you want. And I want to tell you a proof based on the concavity of the profile, based on the concavity. So let's go to the proof. So the proof goes by contradiction. First, take the two functions. Two functions f1 and f2 are just the left-hand side and the right-hand side raised to the power n over n minus 1, right? So on one side you find f1 that is just this function with the AVR raised to n over n minus 1, and it becomes linear with respect to the volume, while f2 is unknown, is just my profile to n over n minus 1. So by contradiction, I want to prove that f2 is greater than f1. By contradiction, let's say that there is some volume where f1 is greater than f2 at that volume. But then, for sure, in between 0 and v0, I can find another volume where the derivative of f2 is less than the derivative of f1 at that volume v1. And the derivative of f1, I can compute it because it is linear. This is just a constant, right? It's just a constant. And now I want to work at this special volume v1. And here I'm going to use another theorem of ours that is the following. It's called generalized existence. And the statement I'm going to tell you is in collaboration with Antonelli and Ardulli, but again, it comes after many insights by many other people, starting from Lyons in the 80s, and then there have been progress by Ritori Rosales, and the crucial one by Nardulli, and then there was even a first generalization in collaboration with Antonelli and Fogagnolo, until we ended up with this theorem that is actually a corollary of the most general one. It tells you, this theorem tries to tell you what happens if you want to solve the existence problem, the existence of minimizer at some volumes. And it's almost a tautology. It's going to say either you have existence or not, basically. But in the following sense, in the following sense, take it so again, non-negative Ricci, forget about these assumption if you want. Fix a volume, try to minimize the perimeter for that volume, right? Well, then either there is an isoperimetric set of that volume, thank you, or there is not. But in that case, there is maybe another space that is again with a negative Ricci, and a set inside that space that solves my starting problem. So precisely, it has the correct volume, and it has the correct perimeter. The perimeter of Z inside the other space is the infimum of the problem in M, my starting space. Why so, and why should you remember this? Because of the picture, because it's very easy, the picture. Why you get this alternative? Because let's try to take a minimizing sequence. Take this M, you take your minimizing sequence omega I, so it has volume equal to V and goes to the infimum, and then you can prove that you have this alternative. If this sequence remains here around inside some compact subset of M, then it's going by precompactness, you know, of a lower semi-continuity of BV function, it's going to convert to some set omega that is going to be isoperimetric. If this does not happen, this means that isoperimetrically, so for the perimeter, it is convenient for this sequence to slide away along at infinity along your manifold, right? But then it is possible to say that this mass actually ends up somewhere. It ends up at a space that you can think it is located at infinity along M. So we will call it a limit at infinity along M. So the mass cannot stay here because it's not convenient, it's going somewhere. Well, you can say that somehow following some sequence of points, it ends up somewhere. And for example, the point here is that even if M is a smooth manifold in general, the space Y is not a smooth manifold. So this is a point where it is necessary to speak about metric measure spaces in this case. And so you have this alternative. Now remember, we wanted to prove my inequality, and we have a special volume V1 where something happens. I try now to apply this theorem at that volume V1. So let V1 the number as before. Now I try to apply my generalized existence theorem at that volume. And in a generalized sense, I get a minimizer, right? Because either I have an isoperimetric set or either I have an isoperimetric set in another space. But in any case, it has volume V, and its perimeter is going to be the profile at that volume, okay? And I don't care where it is, basically. Now, another point, well, okay, you may know that isoperimetric sets in Rn, in manifold, they have constant mean curvature, right? Because they are minimizer of the perimeter with a volume constraint. And it is very classical also, let's say under a smooth assumption, to say that the derivative of the isoperimetric profile coincides actually with the value of the constant mean curvature. This is classical. Basically, we can generalize this concept to say that, so the derivative of the profile, here this is an X, it should be M, the derivative of the profile at the volume V1 of my space, the profile of my space M, in any case is a constant that plays the role of a constant mean curvature. And now, whenever you have a set with whose boundary has constant mean curvature in a manifold with non-negative Ricci, you can actually prove, it's again very classical, to prove upper bounds on the volume of tubular neighborhoods, basically, okay? So the value of the constant enters to play in an integral, and you estimate from above, for example, the volume of tubular neighborhoods. But now, I can estimate from above the volume of tubular neighborhoods, and at the same time, the derivative of the profile at volume V1 is going to satisfy a strict inequality, because here inside F2 prime, there appears I prime M, right? So exploiting that I have a strict inequality on I prime, if I do the integration and I use this strict inequality, Then I can divide by t to the power n, let t go into plus infinity. On one side, I will see the asymptotic volume ratio, right, of my manifold, but the strict inequality is going to give me the contradiction. And so I get the inequality. Now I am also interested actually in the rigidity part of this inequality, and it's going to be similar again. So now we have the inequality, and let's say that I have a set that achieves equality for some volume. Then in particular, the previous two functions touch at that volume, at the volume of E. And now I already know that, remember, F1 is a linear function, F2 is above F1, but it is concave, right? So if they touch at 0, if they touch at some positive volume, then actually they must coincide for any volume. So actually from the equality for some volume, I actually know that the profile of my space is exactly the same is actually given by the function F2. And then I can also discover what is the constant mean curvature for the set E, right? Because E is isoperimetric. I know the expression of F1, I can derive F1 at that volume, and I discover the value of I prime M at the volume of E. That is some expression depending on perimeter and volume. But again, now this number is going to play the role of the constant mean curvature for the boundary of E. And again, we can it is again very, very classical to prove that on a manifold with non-negative Ricci, this fact, so having constant mean curvature, gives you two things. First, an upper bound on basically the largest ball that you can put inside the E. So the supremum of the distance inside the E from the complement is bounded in terms of the mean curvature. And again, so you can do basically the same estimate, but before we estimated the volume of tubular neighborhoods outside, now you can estimate tubular neighborhoods inside. And if you go inside your set E up to this distance, you are going to fill completely your E. And so you estimate the volume with, again, a similar integral as we saw before, depending on the value of the mean curvature. But now if you compute the integral and you use the equalities as before, you discover that actually these inequalities are saturated. And once they are saturated, also the other one is saturated. And so you discover not only that the ball of that radius is contained in E, but also thanks to Bishop-Gromov, you discover that E coincides with the ball, and you discover the volume of the ball, and the volume of the ball of that sum radius is going to be exactly AVR times omega m times its radius to power n. So you are exactly in position to apply the rigidity part of the Bishop-Gromov theorem to discover that actually your manifold is a cone again. Okay, this completes the proof exploiting the concavity. And I want to focus now on actually an open question that remains after we have done this proof. We started with an isoperimetric set, okay, but actually, in the first implication here, in the first item, actually, in order to say that the profile F1 coincides with the profile F2 coincides with the explicit function F1, actually, you just need to know that the two profiles are equal at some volumes. You don't really need the existence of an isoperimetric set, right? So it remains open, the fundamental question of understanding whether, if you just know that the profile touches its spontaneous lower bound, then can you get rigidity? And this is a very nice open question that formulated is the following. Does rigidity follow from equality of isoperimetric profiles? So we are in the first setting. Let's say that for some volume, hence any, you have equalities of the profile with that specific function. Is it possible to say that M is a cone? This is a very nice open question, and this is the typical question that I was trying to mention at the very beginning of the talk, right? If I have a global knowledge of my profile and observe that actually the profile function on the right, in particular, is the isoperimetric profile function of a cone with that AVR, right? So I am saying, if the profile is equal to the one of a cone, then M is a cone. So is the isoperimetric profile, even if you have a global information that has a isoperimetric profile, does this distinguish between two spaces that are very different in their structure? That is open at the level of non-negative Ricci curvature. And actually, just to tell you, if instead your manifold has non-negative sectional curvature, which is much stronger, then the answer is yes. But because actually you can prove existence. This is a result together with Antonelli, Bruet, and Fogagnolo. And it tells you that if you have a manifold with non-negative sectional curvature and positive AVR, then for sufficiently large volumes, there exists isoperimetric set. And so you are back to the previous proof. Once you have existence of a set, I do the computation as before. So this theorem is not really answering to this open problem, right? Because again, it is exploiting existence of isoperimetric sets, right? So the question is a more structural question. Okay, this is for what concerns part one, so the first word of these spaces. And now I go to the second part where we will try to understand very, very similar questions in the spirit. So in the part two, this is, I will tell you results in the working collaboration with a more recent one with Gioacchino Antonelli. And now the picture is going to be the second one, right? So the one of cylinders of something with linear volume growth, at least. Actually, we need to understand whether this picture is correct in some sense, right? It's just a mental picture for the moment. And okay, so let me tell you the definition, because again, we are in general speaking of metric spaces, but the definition is very simple. We are going to say that a space is a so-called Alexandrov space with curvature bounded below by 0. So this is just to replace the word non-negative sectional. If triangles in your space are fatter than Euclidean triangles, right? So you can just look at the picture. I have my space, which again is X and should be M. Take any triangle. So take 3 points and connect them with geodesics. Take another triangle in R2 with whose sides have the same length, and also take a point on one side that divides in the same way the one of the edges. Well, then when I say that my triangles are fatter, I'm just telling you that the distance between that point and the other vertex is larger than the one that you can compute on R2. Okay, so this is the definition. Again, we will never need the definition, but it is this one. And let me just tell you that this is, if you assume non-negative sectional curvature, this is a corollary. Okay, so this is called the Toponogov theorem. Instead, we can, in a generalized sense, we can take it as a definition. So in particular, as example, any complete Riemannian manifold with non-negative sectional curvature is in this class, but also if you want convex bodies in Rn, so closure of open convex sets in Rn are in this class, and also their boundaries if you want, when you endow them with the intrinsic distance on the boundary. And just to tell you, if you are wondering, just like on a smooth Riemannian manifold, the non-negative sectional implies non-negative Ricci, and it is strictly stronger. It is the same in the generalized sense. So first, just to be precise, once you are given a spaces with the curvature bounded below by 0, then it has some spontaneous Hausdorff dimension, okay? Okay, well, so then it is spontaneous to endow it with that measure we always saw before. And then CBB0 implies RCD, so implies non-negative Ricci. These are results by Petruni and Gili Cuvada-Ota. Okay, so in any case, it is a stronger assumption. Okay, so CBB 0. And now, before telling you the second main result I want to discuss, I just need a final preliminary, but we are already familiar with that preliminary because it is about limits at infinity again. So there is this proposition that I don't want to discuss actually in the details. It tells us the following. Look at the picture. I take my space, M, my manifold. Let's say it is RCD or CBB0, doesn't really matter. Actually, here it enters the assumption on the balls that I'm not discussing right now. And do the following. Take a sequence of points diverging to infinity. Consider, for example, PI down here, right? So PI goes outside any compact set. Well, there is a proposition due to Gromov in principle, so it's called Gromov precompactness, a proposition telling you that you can pass to the limit. So basically, the proposition tells you that locally around your sequence of points, eventually the geometry stabilizes in a suitable sense. That is called the Gromov-Hausdorff sense. So in particular, but it's very intuitive. For example, for the sequence PI, around in any ball centered at PI, your space is getting more and more similar to a cylinder. So the limit at infinity in that direction is going to be a cylinder, right? If you take QI going along the end of a cone going to plus infinity, actually a cone is getting flatter and flatter when you go towards infinity. So locally around QI, eventually you see Rn. So in that direction, the limit is Rn. But then finally, let me just tell you that this notion of convergence is very weak. So in general, you don't get a smooth manifold in the limit. Somewhere you can singularize and find, for example, a cylinder over something that is non-smooth, maybe a polyhedron or something like that. Okay. But in any case, this ensures existence of limits at infinity that we gave for guaranteed before, right? So this is the concept of limit at infinity along a space. And now I can tell you finally our main result that is again in the spirit said before. It is a sort of characterization of linear volume growth. So a characterization of the second picture that I drew before. Take your non-compact CBB0 space again with this assumption on the unit balls. Well, then the following are equivalent. First, the fact that the linear volume growth that is clearly codified with this limb soup. Okay, so linear volume growth. Volume growth is at least linear, so this is the requirement that is also at most linear. So it's linear volume growth. Well, this is equivalent to the fact that any limit at infinity is actually a cylinder. This is very intuitive, right? If you think of a cylinder, is obvious. If you think something that is asymptotic, so a cylinder, you go to infinity, you will find actually a cylinder. And actually, it is a cylinder over a cross-section that is unique independently of the sequence of points that you are taking. Actually, this is equivalent to the fact that the whole space is either a tubular neighborhood of a line or of array. So any points has bounded distance from a line that is an infinite geodesic homomorphic to R, or it is any point has bounded distance from array that is instead a geodesic homomorphic to a half line. Okay, so it's exactly more or less this picture, and these are all more or less geometric equivalences. But any of those is equivalent with the fact that the isoperimetric profile is actually bounded, right? That is the first picture we drew at the beginning. So we are sort of relating the global geometry with the global behavior of the profile. Not only you have this equivalence, but you also have rigidity. So in particular, you can say that the profile, which is bounded, is eventually constant. So for some volume is constant, if and only if either your space is isometric to a cylinder, or after you remove an open set, you see the end of a cylinder. So you see 0 plus infinity times k, right? So if you remove a compact set, then you see the end of a cylinder. Okay, so now in the remaining time, I would like to try, the proof is quite long, but I want to give you some ideas of how to prove the implication, basically going from top to bottom, so from the geometry to the isoperimetry, but maybe it's more interesting than to go from bottom to top, right? So from the assumption on the profile to deduce something on the geometry. So let's start from geometry to isoperimetry. And an important simple lemma actually in this context is the following lemma called the splitting at infinity, that tells you that at infinity you split a line. So take again your space with the non-negative sectional in the generalized sense. Take any limit at infinity. Well, limits at infinity indeed split lines. It means that they are isometric to R times another factor. You know almost nothing about the other factor, but okay, they contain a line. They are R times something. Okay, so this is general information, and then you can more or less, it's technical, but it's fairly easy to go from geometry to isoperimetry. So let's start from top. The first assumption is take your manifold CBB0, and suppose you have linear volume growth. I want to deduce something on the isoperimetry. Now, okay, linear volume growth that I will denote LVG actually implies, it's not too difficult to discover it, and then any limit at infinity has again a linear volume growth. But now any limit at infinity is R times something. But if you have linear volume growth also at infinity, the other factor must be compact, right? Then you have to prove the uniqueness of this compact factor, but okay. So this classifies basically the limit, the unique limit at infinity. Also, playing a little bit with the CBB0 condition, you can discover that just the existence of a limit at infinity of that form is enough to deduce that this is equivalent to the fact that the space is a tubular neighborhood of a line or array. And then again, finally, it is again very simple to deduce that the profile is bounded because it is always true that the profile of my starting space is less than or equal than the profile of any limit at infinity, because any set in a limit at infinity, the best one, let's say an isoperimetric set at infinity, can be approximated by sets. So for sure the profile on my space is less than the profile at infinity. But now at infinity I see a cylinder. We said that the cylinders have bounded isoperimetric profile, then the profile is bounded, right, of my starting space. Okay, so this was from geometry to isoperimetry. Let me tell you some words for the other direction, because it exploits some classical estimates. And so now we take again our space, and now we assume that the profile is bounded. The profile is bounded. So what do we do? The goal, for example, is to prove an alternative. I want to prove that either the space has linear volume growth or a limit at infinity has linear volume growth. And thanks to the splitting at infinity, I actually discovered that the limit at infinity is r times k, and I already know that this alternative is actually an equivalence. So I am proving two equivalent things. But it is easier to prove the alternative. So we will say that one is false, and I will prove the other. So either M has linear volume growth or a limit at infinity has. So there is a classical estimate due to Coulomb sum of cost that can be generalized to this setting that exploits actually the behavior as a function of R of the infimum of the volume of balls of that volume. If you take that function, call it W, and consider the generalized inverse, okay, this is increasing, let's say that it has an inverse function phi, then you can use phi in order to bound from below the profile in this way, as said by Coulomb and sum of cost. But now if the profile is bounded, here the left-hand side is bounded, so phi is at least a constant time the volume, but then W is the opposite because it is the inverse. So I discovered that W has at least linear volume growth. And W is not exactly the volume of ball of radius R in the space, it is the infimum. So, but it is already a hint that volume of balls in my space are growing at most linearly. But this is just the infimum again. So now I try to prove the goal. So let's say that M has not linear volume growth. So let's say that there is a sequence of radii such that for a fixed origin, the volume of ball of those radii over Ri goes to plus infinity. Now let's fix those radii and consider points Pi almost achieving the infimum in W for those radii. So consider Pi such that the volume of a ball of radius Ri is almost less than the possible infimum. And I already know that the infimum is less than constant times these radii Ri that are going to plus infinity. You can also deduce that Pi diverges along M, because otherwise, if it stays there, then actually you imply that M has linear volume growth, but we said it's not the case. So, okay, now I have finally points going to infinity. I want to discover something at infinity. And balls for large radii centered at those points have volumes linearly bounded. But these are only for some specific radii. But after you know this for specific radii, again, it is an exercise to find some points, let's say close to Pi, such that not only for that radii Ri you have a linear estimate, but actually for any R in between 0 and let's say Ri over 4. So now you find Qi close to Pi, so going to plus infinity, where actually balls of larger and larger radii always have a linear bound on the volume. You pass to the limit. Qi is going to be in a limit at infinity. The estimate passes to the limit, and you will find that a limit at infinity has a linear volume growth. Okay, so finally, we also had rigidity in the statement. So again, I will tell you something about the proof of the rigidity, which is again very similar to the previous case. We want to exploit a theorem that implies rigidity. That is a generalization of a theorem of Kasue, the generalization done by Ketterer, Kitabeppo, and Laxian very recently, which exploits techniques from Gigli. And it tells you the following. Basically, it tells you that whenever in a space non-negatively curved, non-compact, you find a minimal surface, then outside the minimal surface you will see a piece of a cylinder. Okay, but we can state it for isoperimetric sets. Let's say that you have an isoperimetric set, and assume that you know that the profile at that volume is equal to 0. This is, as I said before, the derivative of the isoperimetric profile plays the role of a mean curvature, right? So we are basically saying that the boundary of this set is minimal; it has 0 mean curvature. Well, then you can generalize the Kasue rigidity to tell that either the space was already a cylinder, or if you remove E, you see the end of a cylinder. So our goal again becomes, if I want to prove rigidity was if the profile is eventually constant, then I am either a cylinder or I see the end of a cylinder. Again, my goal becomes to prove existence of isoperimetric sets for volumes such that I see 0 derivative of the isoperimetric profile. So let's let's assume the rigidity assumption. So let's say that eventually IM is constant. And my goal becomes, I want to prove existence of isoperimetric for large volumes again, because for large volumes, IM is constant, so the derivative is going to be 0. Exactly. And again, this is technical, but you remember the generalized existence theorem. It tells me that if I want to prove existence, I just need to exclude that my mass, my minimizing sequence goes away to infinity, right? So I need to avoid that behavior. And this can be done, for example, by comparing, by finding that on your original space, you have a better competitor than the isoperimetric profile in the final space there. So you discover that it was actually not convenient to go away to infinity. And you can find such competitor exploiting the so-called Busemann function that I will not maybe define now, but they are, again, a very classical tool in this topic. And what do you do? Let's say that M is a tubular neighborhood of array, because otherwise it's a cylinder and it is already a rigid space. So let's say that it is a tubular neighborhood of a cylinder. So I am in this picture here on the right. I am the tubular neighborhood of a cylinder. And I take this Busemann function of the ray gamma. Again, I don't want to tell you what the Busemann function is, but the point is that the level sets of the function, of the Busemann function, they are, let's say, a sort of exhaust. You can prove that they are a sort of exhaustion of your space, and they approximate basically the coordinate R on the final cylinder that you will find. So sublevels are sort of an exhaustion here. And so as these sublevels are approximating, so pieces of the final cylinder that you will find at infinity, let's say that R times K is the final cylinder, the limit at infinity that you will find. If you play enough with the CBB0 condition, you will discover that, again, sub-level sets of this function have perimeter that is less than the volume of the cross-section of the final cylinder. And now I want to convince you that indeed this sublevel is a better competitor with respect to large isoperimetric set in the final cylinder, so that this implies that it is not convenient to go away for a minimizing sequence. And this is now a very simple inequality. So let's say, if you want by contradiction, that you have no isoperimetric sets for a volume V that eventually is going to be large. But then the alternative tells me that there is a set in the limit at infinity that is R times K, okay, of that volume, with the perimeter equal to the profile at that volume V. But now I am in a cylinder again. Now Z is contained in a cylinder. And if now I take V very large, you can prove that on a cylinder, isoperimetric sets are exactly slabs of cylinders, so pieces of cylinders, as I drew before, okay? So in particular, for very large volume, the isoperimetric sets in a cylinder have a perimeter equal to 2 times the volume of the cross-section. But now I already know that a suitable set, that is sublevel of the Busemann function, it has perimeter less than just 1 time the volume of the cross-section. So you couple these together to derive a contradiction, right? Because the volume of the cross-section is greater than the profile of the volume V, because this is a limited infinity. This is equal to the perimeter of Z, but by definition, this is greater than the profile for a large volume in the cylinder, and this is going to be twice the volume of the cross-section, and you get your contradiction. And now I want to conclude again mentioning open questions. Because again, we are sort of, in a sense, cheating, right? Because once again, yes. Exactly. Yeah.
Sorry. I mean, what can happen if you allow for that?
Okay, there is actually a proposition. Maybe if you want later, I can discuss this more. But there is a proposition that tells you that under non-negative Ricci, if this infimum is 0, actually infimum equal to 0 is equivalent to isoperimetric profile constantly equal to 0. So basically, your variational problems becomes useless, becomes degenerate, right? You're not very interested in that case. This is from the variational point of view. From the geometry, that maybe was more your question, what happens is that this, do you remember the pre-compactness theorem I said before? This assumption is enough to tell you that limits at infinity basically have the same dimension of the space you were starting with. Otherwise, as probably you were thinking, you can degenerate it. For example, you can squeeze a cylinder, and that maybe a two-dimensional thing becomes a one-dimensional object.
Exactly. Okay.
So yeah, so this latter fact is the influence of this assumption on geometry, while on isoperimetry, the point is that the variational problem becomes non-interesting.
Thank you.
Okay, so the very last slide about open problems, I said, because in a sense, again, I am cheating in the sense that, okay, I am assuming a global assumption on the isoperimetric profile, right? But in order to prove rigidity, I am proving existence of isoperimetric sets, which, okay, I mean, I am allowed to do this. But but in this proof, it crucially plays a role the assumption of having CBB 0, right? So curvature bounded below by 0. And this was the assumption, the assumption in force for the second part of the talk, right? While in the first one, there was only the non-negative Ricci part. And so you can ask, okay, what happens into the second part if you put non-negative Ricci? Actually, it becomes more difficult, and a few things are just false. For example, the lemma we started with, the splitting at infinity. The splitting at infinity is just false in general, in general, in the sense that there exists a manifold built by Kazu and Washio in the 90 that is not isometric to R times something, but a limit at infinity along a suitable sequence of points is the space itself. But again, it is not isometric to R times something, so the limit at infinity, which is itself, does not split a line, right? So even the first lemma is not true in general on a negative Ricci assumption. And so I want to conclude with the open question. If you replace the assumption of having curvature bounded below by 0 only with the RCD assumption, so non-negative Ricci, and again, you assume this assumption on the balls. Is it possible actually to do the implication isoperimetry implies geometry? So if the profile is bounded, is it possible to say that the space has linear volume growth? And do you have rigidity? So if IM is eventually constant, is it true that the space is a cylinder or splits a cylindrical end? This is again an open question. And okay, so this is what I wanted to say. So thank you for your attention.
Thank you very much, Marco, for your talk. Questions?
About the very last question, if you had some sort of, because this is true with the non-negative sectional, right?
Yeah, the rigidity part.
Yes, if you have a non-negative Ricci curved manifold and the sectional curvature decays in some way, it's easier to answer. Do you know if this is true?
No, I don't know if this is true. No, and
that manifold there, I don't remember. As the sectional curvature going to 0, yes.
Well, actually, if you do this sort of translation, right, you replace t with t plus t0 and you leave rp constant. This is an isometry, right?
Yes.
So actually, if you translate towards on the right, the sectional is constant,
exactly,
right?
exactly.
So it's not going to 0.
Okay, so it's not
no, exactly.
Okay. Thank you.
More question?
Okay, so when you have the alternative between either you have a optimal set or some other space with the optimal set, how do you construct this space at infinity? Is like it depends also on the sequence or not?
Yes. So you don't really construct the space at infinity, right? You use the Gromov precompactness proposition, telling you that after I identify a sequence of points and I discover that the volume of my set follows this sequence of points, then I can extract a subsequence such that somewhere you will converge, definitely, okay? Because this is just the result of Gromov. So I don't construct the set at infinity. I rather discover that the volume accumulates somewhere, right? And this is based on a so-called concentration compactness principle, okay, which is indeed in principle due to Lyon's, and that's why in the 80s.
This assumption on the lower bound for the volume of geodesic balls, this kind of rules out N's finite volume, no?
Right.
So is this a purely technical assumption, or is the statement false without?
Well, again, it depends. Yeah, the statement is false, or I mean, you have to change the statement, right? As we said before, both because limits at infinity may have less dimension, okay?
Mm-hmm.
So first, but also because the isoperimetric problem becomes trivial, and you always have non-existence in that case, right? Because the profile is 0. But then, okay, if you have at least a Poincare inequality, any set with positive volume is going to have a positive perimeter. So the problem becomes just trivial. It is, I would say, a spontaneous assumption in this problem.
Yeah, okay.
But I can tell you that, for example, in dimension 2, you can forget about this assumption because it is automatically true under non-negative Ricci or sectional assumption, for example, in dimension 2.
Okay, other question or comments? So if not, we thank Mark again. And
Thank
we
you.
thank all the other speakers of all this workshop for a very good job.
Yeah, and one last thing in the name, I believe, of all the speakers, let me thank our organizers for their job, and also the staff, of course. And please go on with this saga of Pisan Workshop in geometric analysis. Thank you.
I continue with what Mark was saying. Clearly, the workshop was not possible without the opportunity to use the Centro de Giorgi for all the work of the staff. And I'm really happy that also this year we had these very nice talks by all the speakers. And we hope to see you all also next year. Thank you.
Thank you all.